Good morning everybody. In this class we are going to discuss about the interaction of the radiation with atomic system, and to describe the interaction between the radiation and atomic system, let us consider two energy levels, E1 and E2 of an atomic system. Okay, where the number of atoms per unit volume in E1 energy level, say N1, and number of atoms in the E2 energy level per unit volume is N2. When a radiation of frequency corresponding to the difference of two energy values incident on the atomic system, it can interact in three distinct ways, and the name of the interactions are stimulated absorption. Okay. Number 2, spontaneous emission of radiation, and third, stimulated emission of radiation. Okay. Now, first of all, I will discuss about stimulated absorption. When the atoms remain in the lower energy state and radiation of energy H nu is equal to E2 minus E1 incident on the atomic system, then the radiation will be absorbed by the atoms in the lower state and go to the excited state. Okay, and the rate of absorption at the lower state is depends on the number of atoms in that energy state and also the energy density of the incident radiation. Okay, if the energy density of the incident radiation in the frequency interval nu to nu plus d nu is E nu d nu. Okay, this is the energy density in the frequency interval nu to nu plus d nu. Then the number of atoms undergoing through absorption for unit volume per unit time can be expressed as gamma 1 2. This is the number of atoms going through stimulated absorption, and this is equal to the B12 number of atom in the lower state and the energy density in the unit frequency interval. Okay, here B12 is the proportionality constant and it is also called Einstein coefficient for absorption. Now I will discuss the spontaneous emission of radiation. We know the atoms in the excited state do not stay for a long period of time. They stay in the excited state very short period of time, about 10 to the power minus 8 seconds, and they make a transition from excited state to the lower state and release a photon, and the direction of the emitted photons are moving in a different direction. They move randomly Okay, and we cannot control this type of emission, spontaneous emission, we cannot control it. Spontaneously emission takes place. So this type of emission does not depend on the incident radiation, but depends on the number of atoms in the excited state. So the number of atoms make spontaneous emission per unit volume per unit time can be written as gamma 21, here transition from excited state to the lower state E1, and this is the number of atoms make spontaneous emission per unit volume per unit time is A21 into number of atoms in the excited state. This type of emission does not depend on the energy radiation, and this is also another proportionality constant, and this is called the Einstein coefficient for spontaneous emission of radiation. Okay. Now another one is stimulated emission of radiation, and this is very important. Actually, this type of emission of radiation are used for the lasing action, and also we have discussed in the previous class. Okay. Actually, when the atoms remain in the excited state, they make transition in a two distinct ways. One is spontaneous emission of radiation, and another one stimulated emission of radiation. Stimulated emission of radiation takes place when the atoms remain in the excited state, and in that case emission takes place under the action of the electromagnetic field of the incident radiation. So stimulated emission of radiation depends on the incident radiation and also the number of atoms in the excited state. Okay. So the number of atoms make stimulated emission of radiation per unit volume per unit time can be written as prime equal to B21 into number of atoms in the excited state, and this is energy density. Okay. This is the expression of the number of atoms make stimulated emission of radiation per unit volume per unit time. At thermal equilibrium between the incident radiation and the atomic system, the rate of upward transition from lower state to excited state and rate of downward transition from excited state to lower state are equal. Okay. So at equilibrium we can write, actually this is the upward transition. So at equilibrium gamma 12 is equal to gamma 21 plus gamma 21 prime at thermal equilibrium condition. Now substitute the values of gamma 1 to gamma 21, gamma 21 prime is B12 N1 Nu equal to A21 N2 plus B21 N2 U or U equal to A21 N2 divided by B12 N1 minus B21 N2. Okay. Now both numerator and denominator are divided by this term, then we will get A21 by B21 equal to B12 by B21 into N1 by N2 minus 1. Okay, so this is the expression of the density, energy density of the radiation per unit frequency interval. According to the Boltzmann statistics, we know the number of atoms in the excited state, that means in the E2 state, can be written as number of atoms in the lower state, here E1 exponential minus E2 minus by kT. Okay, here K is the Boltzmann constant and T is the absolute temperature, or N1 by N2 equal to exponential minus this will be plus when we divide by N2 and this expression come in this side, so we will get E2 minus E1 by kT, and if we consider the frequency of the incident radiation is equal to the difference of the two energy values, then we can write E is equal to H nu is the energy of the incident radiation, H nu by kT, and this is equal to N1 by N2. Now substitute the value of N1 by N2 in this expression, then we will get A21 by B21 into B12 by B21 exponential H nu by kT minus 1. So this is the energy density of the incident radiation per unit frequency interval. Okay. Now we have from Planck's law the energy density of radiation per unit frequency interval E nu is equal to 8 pi H nu cube by C cube H nu by kT minus 1. This is equation number 1 and this is equation number 2. If we compare these two equations 1 and 2, then we get here the coefficient of exponential H nu by kT is 1, but here B12 by B21, B12 by B21 is equal to 1. So from this expression we can say that actually this is the Einstein coefficient for stimulated absorption, and this is the Einstein coefficient for the stimulated emission of radiation. So the rate of stimulated absorption is equal to the rate of stimulated emission of radiation, and also from this derivation we get B12 by B21 A21 by B21. Here the numerator is this and in the expression numerator is this, so this will be 8 pi H nu cube by C cube. So this is the relation between the Einstein coefficient for Einstein coefficient for spontaneous emission of radiation, and this is the stimulated emission of radiation. Okay, and we can show this is equal to exponential H nu by kT minus 1 when the frequency of the radiation is greater than H by kT, this is always plus. So the rate of spontaneous emission at thermal equilibrium condition is always greater than the rate of stimulated emission of radiation. Okay, thank you.